In this lesson, we're going to talk about the semantics of programming languages. I'm going to give the semantics of our programming languages and the paradigms we see. So the first question about semantics is, why do we need it? Why do we need to have this kind of an understanding? Well, actually, it's very simple. If you do not understand something, you do not master it. It masters you. Couple of examples. If you do not know how a car works, then if you have a problem with your car, then the car mechanic can tell you whatever he wants and charge you whatever he wants. If you do not understand how government works, then you cannot vote wisely, and the government might go in wrong directions and become a tyranny. So understanding is important, and the same holds true for programming. If you want to write correct programs, if you want to understand other people's programs, you have to have a deep understanding of the language. So all software developers should have this level of understanding. So the goal of the lesson is to show you how. You see, it's not really that complicated. You don't have to be a mathematical genius to understand programming languages. You just have to have a little bit a bent for precise thinking. And probably all programmers already have this kind of a talent. So what is the semantics of a programming language? Well, the semantics, or formal semantics, or mathematical semantics, is a completely precise explanation of how programs execute, and we can use it to reason about program design and correctness. So we are going to give semantics for all the paradigms of this course. So we're going to start by giving the semantics of our first paradigm, which is functional programming. Our semantics will consist of two parts. We have already seen the first part, which is the kernel language. And in this lesson, we're going to see the second part, namely the abstract machine. And together, they form the complete semantics of the functional paradigm. And later in the course, we're going to extend this with the new concepts for the other paradigms to get the semantics of all the other paradigms. Okay, before we take the plunge and look at the details of the abstract machine, let's take a step back and talk about semantics in general. So, just to give a very brief overview of the area of programming language semantics. So, how can we define the semantics of a programming language? Well, four general approaches have been defined for this. One called operational semantics, one called axiomatic semantics, one called denotational, and one called logical semantics. And each of them has its own way of looking at things. So let me just briefly try to tell you what the essence, the gist of each of these approaches is. So the operational semantics, the name says it, it's operations. So we're looking at an abstract machine. We're looking at a kind of simplified, mathematized execution on an abstract machine. The axiomatic semantics is talking about properties, which is where the word axiom comes from. So if a program starts with something being true and then it executes, something else will be true after. So we have the before and after. So program is an implication. If the before properties are true, then the execution of the program gives the final properties. And this approach of implication, before, after, is used at all levels for single instructions, for procedures, for bigger parts, and also for the whole program. And the before is sometimes called precondition, the after is sometimes called postcondition. So that's axiomatic semantics. Denotational semantics is more mathematical. It's more looking at a program in an abstract way as a function, not over integer lists. No, a function over an abstract domain which somehow models the knowledge of what the execution is doing. So loops will be fixed points in this approach. Function composition will be composing the programs in some way. So you can manipulate the programs using the techniques of mathematics that apply to functions over this abstract domain. So this is a more abstract way of looking at programs. And finally, the fourth approach is called logical semantics. Here we're looking at logic in the sense of first-order logic or predicate logic, logic in the sense of reasoning about truth And so a program is considered to be a model, a logical model of a set of axioms. What that means is that what the program does is going to be in agreement with some logical axioms. So if I have a sorting program, then one of the axioms might say that certain elements will be less than certain other elements, or a list is sorted. These are logical properties. So the execution of a program in this model is actually deduction. The result of the program is going to be a true property derived from the axioms. Okay, so those are the four approaches. We are going to use the operational semantics approach in this course. It has the advantage that it works for all paradigms because all programs have to run. So this works for all paradigms. The other approaches are more targeted. They're less general. They work best for some paradigms. Like axiomatic semantics works best for imperative, where you have updating of variables multiple times. Well, there you have a sequence of updates. So axiomatic semantics works well when programs are like sequences, whereas denotational semantics works well in functional, pure functional paradigm, but does not work so well if you have imperative paradigms. And logical semantics works well, of course, when your program is based on logic, like logic programming or Prolog or constraint programming. So we are going to use operational semantics, but the operational semantics approach has a disadvantage that it's focused on the execution and not so much on the properties. So what we are going to do is we're going to start with operational semantics, and we will extend it a little bit by talking about the properties during the execution. So we'll add a little bit of the other approaches to the operational semantics, but the core is still an operational semantics. So the operational semantics has two parts. Has a kernel language. So we take a program written in a practical, very complicated language and translate it into a simple kernel language. So this simplicity is very important because it means that the abstract machine, which then executes the kernel language, can be very simple. So the kernel language is very important for the operational semantics approach. And in this lesson, we're going to do several things. We're going to start with an example. We're going to an example about how to prove correctness using operational semantics. So we're going to execute the program in the abstract machine and show that some property holds. And then we will have another piece of the lesson where we'll actually define the abstract machine and give an example of how it works. And then we will define the semantic rules. So each instruction in the kernel language has a rule, a small definition of exactly how it works in the abstract machine. So basically, you have to have one semantic rule for each instruction in the kernel language. So we're going to look at that. And then finally, we're going to take a special look at procedures, procedure definitions, and procedure calls, since this is very important. Like we saw in higher order programming, procedures as procedure values are really the foundation of very many powerful ideas, including data abstraction. So it's a good idea to look at that a little bit more closely.